Record on the computer. Okay, good evening, everybody. It is Tuesday, March 23rd, 6 p.m. The course is MED110, Anatomy Physiology, and I'm your professor, Dr. Garais. And what is due this evening? Your task one, discussion one, lesson one. Well, specifically, it was due at 6 p.m. If you can get it to me by tonight, we're only going to chop off 10%. But if you start going into tomorrow evening, again, for it, really, you gotta think about time as a commodity and something really important, because in the medical world, have any of you taken what do you call that, CPR yet? And if you have,
I have.
Then what is the golden 5 minutes?
That's the time you have to save their life.
Yeah, well, it goes, not save their life, because we don't save people's lives. It's more of a, it's more of a management thing. It's the minute, it's 5 minutes, because in CPR, you have a 54% chance of reviving the person. So that person's already in trouble. So you're, the golden 5 minutes is that if there's cardiac and or respiratory arrest, my patient after 5 minutes will have irreversible brain damage. And that's why, what do you call that? People in the medical world have a thing about time. Okay. And for those of you who are going to nursing, that's a serious thing, because remember this late thing that we have, our late protocols. There are many professors who don't have that. It's either on time or it's zero. So please. But for me, for every section that it's late, like for now, you didn't submit it in by 6 o'clock. Submit it within the next 24 hours, and it'll be only minus 10%. And I have to be a little bit more strict with that, because in the past I've been like, get it to me when you get it to me. But we've been getting a lot of complaints from the School of Nursing, and also they're failing you guys in droves. Today's SOS meeting had a dozen F grades from last term, meaning that many of these students will either be removed from their School of Nursing, or they have one more chance. Please don't be that person. The majority of the meeting today was about nurses who are failing out of their program. And now that there's more of you, they're okay with losing more of you, because remember, the Board of Nursing only wants the best at the very end. Meaning to say is people who will pass the NCLEX. And if you can't do your discussions and tasks and lessons on time, it's usually an indication of poor time management. And it's usually somebody that isn't prepared or isn't ready to go to nursing. And again, back to the golden 5 minutes. So please moderate your time. And actually, someone asked me who didn't get accepted to nursing because of their GPA. Someone asked me, how do I get better grades? And it's all simply due diligence. If you work on something daily and prioritize this, and I know it's hard. All of you who have children can't tell me about kids. I got 6 of them. Okay, even though 2 of them are already adults, I still got to worry about them, and they still take up my time. Because all of us also have jobs, money problems, emotional problems, mental health problems, physical ailments, right? But here's the thing, we're medical professionals, and we got to get this stuff on time. So please, while it's still early in the term, you don't want to be repeating this course for 2 reasons. 1, you want to move on with your day. 2, it'll cost you. So again, what's due tonight? Well, not tonight, it was due at 6 o'clock. So if you did not perform your task 1, discussion 1, lesson 1, you'll see currently there's a 0 in your grade. But then do something about it, and then I could award you at least 90% of the credit. It goes if it's 100% A work. But If you hand me 80% work, then I got to grade you 70, okay? And it's utilized as a deterrent, so it can help you with your due diligence and help you with your discipline, because you're gonna need it. So what are we doing again today? Well, we're gonna be doing things until like around 7:30. Around 7:30 p.m., Ms. DeLeon will be talking about APA format, which some of you need to also, brush up on and improve on if you look at the comments of your discussion posts. Now, if I wrote a comment to your discussion post and said, hey, go fix this, if you fix this, in a timely manner, like a day or two right after I post, then sure, I'll give you full credit. But don't wait until, I put in a 0 or something like that. Always monitor your comments from your professors, because it tells you where you are. Because you need to know, it goes on a daily to weekly basis, where you are in the class. And if you don't, please give me a call so I can walk you through it. Alrighty, so right now, what are we doing? Let me see, a couple of people also got on the call. I have to write that down. Because again, attendance on Zoom sessions is mandatory, and also the attendance on the future laboratories, which I'm going to be posting. And again, I will announce the laboratory. The laboratory days are, let me look at my paper here. The laboratory days are Tuesdays, 6 p.m., May 4, May 11, and the final is Tuesday, 6 p.m., May 18. 4, 11, and 18 will be on campus. And I'll also put that in writing as well when we get closer to May 4. Okay? So that's now twice that I mentioned it. So please try to look ahead, try to plan ahead so that you can be on campus, because hey, the laboratories, you guys paid for that. So it's kind of important. Why are we going through chemistry today, which is the topic for today? Well, and last week we were talking about the cell, because we know, right, chemistry is dealing with, how all of these subatomic particles, atoms, molecules, and macromolecules all get glued together. Didn't you ever wonder why, when you jump in a swimming pool or you jump in a shower, why you don't just disintegrate, why you just don't fall apart? But why, when I throw a ham sandwich into a pool, it just disintegrates and falls apart? Because there are bonds. There are things that are keeping us all together. And that's what a bond is. It's like a glue. Or if you watch the video already for this week, they talk about forces and relationships. And if there's a problem on that level, don't you think there's going to be a problem at the organelle level, which we're going to be talking about next week? All the little things that are inside the cell, that's what an organelle is. Then if there's a problem with the cell, there's going to be a problem with the tissues. Then there's going to be a problem with the organs, and then there's going to be a problem with the system. And that's when the patient gets to see us, when they already have systemic or multisystemic problems. So you need to understand, before you get into your pathology class, you need to understand how this all works and how this contributes to abnormal, which contributes to disease. So let's jump right in. And the task 2. Now for next week, we're going to start doing concept maps. If you're not familiar with a concept map, please give me a call or Google it on how to do one and how to do a neat one. I can no longer accept paper ones or ones that you guys take picture of, because they're just, I don't know, they're just really not professionally done or academically sound. So you really need to use Microsoft Word or something similar, or and it really has to be neat. I tried for the last couple of terms to accept like paper ones where people used like maybe a ruler and some paper, but it just comes out really bad. And your future professors, if they have a concept map, they won't accept it either. Took a brief survey of the other professors, and they were looking at me like, why would you accept handwritten homework I got a comment from another nursing professor, quote, "This ain't high school." And I felt bad about that. So in a way, I'm not, because we got to step up our game this term. So, and give me a call so I can show you how to do this. Now, what are we doing? Now, concept maps are easier to make, and they're better because they give a visual representation of the organization of the lecture or the organization of the things you need to learn. So if you look at this, we're gonna look at four things: the basic chemical structure of an organism, macromolecules, bonding, and water. So the first one is basic chemical structures of the structure of an organism, and that's what these videos were talking about. So let's look, and if you look at here, what's an element? What's an atom? Chemical bonds, what are chemical reactions? And then we're going to talk about the macromolecules, and that's the inorganic and the organic compounds. Now, inorganic means that, you know, it's like salt, lead, you know, things that you find in the earth. But organic compounds are living things. And the four, and we're going to be looking at some of these really nice Carolina notes here, which is proteins, fats, and carbohydrates. Essentially, the human being is made up of carbon, hydrogen, oxygen, and nitrogen, all with specific bonds. And those are your organic compounds. So that'll be the macromolecules. And of course, bonding, we already mentioned that. And there's a nice study guide here for water, because we're going to talk about the really neat chemical properties of water. And it makes sense that that's important to us because guess what? Human beings are made out of two-thirds water, and the rest of the dry parts are carbon, hydrogen, oxygen, and nitrogen. So that's what we're going to be doing today. And the concept maps, right? Will, like, let me just give you a brief example for those of you who you know, haven't looked up what a concept map is. So I could Google it, concept map, and let's make it anatomy. So if you look at it here like this, if you look at like the concept map, whatever the main topic is, you have a whole bunch of subtopics. So today would be what? Like chemistry, right? And then all the little subtopics, the four subtopics that we talked about, which is the bonds, inorganic, organic compounds, and then whatever is part of the subtopic, then that'll lead to things. And if you look at this in a way, doesn't this look, if you could look at this, doesn't this tell me actually exactly what's important and how can I ask a question? For example, if I'm going through body systems, I'll have muscular questions, urinary questions, circulatory questions, digestive questions, right? And if you look at all of this, each one has at least two arrows which point to some sort of structure, right? For this one, for circulatory, it's heart. And then for digestive, it's stomach. And then the second part would be some sort of function. Like, look, digestive system, absorption, right? So doesn't that make sense? Now it gives you a greater organization of every little thing you're looking at. And that's the function of a concept map. Concept maps are also good in memorizing protocols. As future nurses, as future medical professionals, there is a pathway or a protocol for everything in the hospital. Here's an example. Let's show you how. Another word is flowcharts, right? So, like in the hospital, everything has to be done in a certain way, in a certain path. And flowcharts / concept maps can lead you to things like, it goes, does my patient have a reservation? No. So they're just visiting, right? And then yes versus no. It tells you exactly what to do. But if yes, we go down this path. I check in the patient. Then I check the purpose of their visiting. Then I check the date. Then I check and confirm the schedule. And you have to do it this same way the entire time, because, and also for legal reasons, everything in the hospital has to go the same exact way, every day, all day, the same way. Okay, I could see now there's more people on. Let me check to see if, and whoever is on the iPhone, kindly, what do you call that? Shoot me a chat with your full name so I can get you in there. So I'm counting now 10 students. Before I had 7. So let me see who else came on board. I got number 8. And Ms. Massey, I already got you. I already got you. I already have Miss Crimes. Okay, whoever's on listed as cell phone, kindly shoot me in the text or the chat, and I could log you in. All right, so let's start. Like I stated earlier, actually, because this is a really nice video, but I'll leave that to you guys. If you go into the lesson 2, there's a lovely set of notes. If it's still there, I think it's in here. Yeah, it's the case, which is a PowerPoint. Which, by the way, I'm going to open up this PowerPoint. Which, by the way, your discussion 2, they talk about this PowerPoint. In discussion 2, it talks about an Alzheimer's case. If you go to the end, the very end of this PowerPoint, which is slide number 45, this is the case study that they're referring to for discussion 2 for Alzheimer's, and we're going to be talking about that later. So let's start. So we already now know the importance of chemistry. Chemistry talks about the relationships between atoms, and we're going to talk about what is an atom. Atom is your smallest building block of who you are as a human being. And the way atoms and all these things, the way that you don't just fall apart is because you're actually feeding the energy that is required for all these bonds or these chemical relationships and chemical processes to work. It's the reason why the second you stop breathing, you'll fall apart. The second you stop eating, you'll fall apart, because if you stop breathing, you no longer have oxygen to feed into the processes. And if you have no longer any fuel, of course, what happens when you're dead? You start to decay. Same thing with breathing. Oxygen is also very important. So oxygen and glucose, it's the 2 purest things that your body requires. And we're going to talk about next week how oxygen and glucose together is the basic fuel of the human body to stay alive. So let's look at this. I don't know. I don't like this thing in the front. It's kind of corny. So let's look at an atom. Now, an atom is composed of, in the middle, it's composed of a neutron and a proton. A neutron is neutral, right? And a proton is, let me see if I can get a better picture. There you go. So if you look at and the anatomy of who you are at the most basic level. So the atom is your basic building block of of a life form or of matter, which is, you know, the rocks and the dirt on the ground, the plants and everything, right? So in the middle, you have protons, which are positively charged, right? You have neutrons, which have no charge, okay? And you know, charge like a battery. And this also shows, if you've ever watched the movie The Matrix, remember in The Matrix, they were talking about how, like, what do you call that? what do you call that? Where they were talking about like a human being is simply a battery. Well, this also hints at us on how we as human beings conduct electricity. You need electricity. It's what powers all your nerves. It's what powers your heart. So you see there's pluses and minuses, and there's going to be a relationship with these pluses and minuses. And we already know that relationship if you've ever had earth science in like high school, where they remember when we had magnets and there's a positive side and there's a negative side, and there's a force there, there's an attraction there, or a relationship there, right? So a typical atom has neutrons, which are neutral, protons, which are positively charged. And at the end, in these rings of energy, right? And the outer ring is called a valence, right? You know, and valence, another word for it is like curtain. You know how the curtains are like they're in layers? Well, the outside curtain or the outside valence is your valence electrons. And electrons are negative. So when we're looking at this, and let's go now that we know what an atom is, the basic building block of who you are. Go back to that PowerPoint. You can see here in sodium, right? You have 1, 2, 3 electron shells, and the electrons, right, which is these red dots, are distributed outside. And the last one is called a valence. This is called your valence electron, and this is your valence energy level. So these are just energy levels where the electrons live. Okay, I don't like that corny. Let's just, you guys are adults. Okay. So now the one thing that electrons like to do is, and oh, by the way, this is your part of your lesson. There are questions here that are, what do you call that? That you have to answer, and we'll kind of answer them together. And you know what? How's this? Everyone on this call, you guys, since I got everyone on this. Everyone on this call, you don't have to do your lesson because I'm gonna pretty much answer your questions that are here. But these are nice questions because these look really nice for an exam, don't you think? So, all atoms, in order for them to be in a neutral state, these valence electrons have to be full. Now, the answer, which one is chemically inert? Well, the answer here is argon. And I'll tell you why. Do you see the valence electrons? There's like pairs. They're all paired up. They're all even. But if you look at oxygen, which is a -1, which means that its outer electron has one extra electron. Its outer valence has one extra electron, right? Fluorine here, you can see this one's missing, right? Lithium, right? This one's all alone. Lithium is highly reactive. And if you guys know anything about lithium, lithium is the drug that we use for bipolar medication, and it's highly reactive to the brain, and it causes a lot of problems. So if I told you this one's missing one, right? So this one will be, it goes, this one won't have a even energy, right? And if you have anything more, if you have more electrons, right? Like oxygen, like lithium, well, actually lithium is, well, oxygen is better. If you have less electrons, right, you'll be more positive. If you have more electrons, you'll be more negative. So lithium is what, 3+? Here's 1, 2, 3, right? Oxygen is -1. So if you look at this, it's uneven. These are all like onesies. They don't have, it's not even. You could look at this one, the argon, it's all paired. So if the energy is at a nice low level, it's not going to want to interact with anybody. So something like argon would be chemically inert, and it's actually one of your it's one of your noble gases which doesn't react with anything. But I can tell you right now, right off the bat, lithium and oxygen, they react with everything. Lithium is 3+. That means it has three. Well, here you'll see these three extra electrons, but it's missing. You'll learn more about that in chemistry. Just know that anytime you see like Na plus, let me write it down. When you see an ion, and you've seen ions before written. So sodium is Na plus, right? That means it has one less electron. This is reactive, right? But argon, it doesn't like to react because it has low energy. The valence electrons in its outer shell are even, and that represents low energy. It doesn't want to react with anything because it's all paired up. But sodium, if we looked at that sodium earlier, you got this one sticking out, right? And that's Na plus. So if you see something like this, and it's usually, what do you call that? As like that, right? So sodium, chlorine, right? These are ions. These are charged particles. They're charged particles because if it's a plus, that means they're missing an electron. If it's a minus, that means they have more electrons than they need. And that's dependent on how many protons are in the nucleus of the atom. So when we see stuff like sodium and chlorine, right? Sodium, if I threw sodium powder into water, it would explode because it's highly reactive. It has that charge on it. So, and also, do you see how a plus one could be attracted to a -1? Remember what we talked about earlier when we talked about magnets and how opposites attract? Now, if I threw argon in an aqueous solution, it would do nothing. It would just sit there. But if I threw something that was reactive, it will react to it. Now, what does all of this have anything to do with the human being? Well, reactivity and attraction. Attraction deals with the bonds that we were talking about. Why is it that when you jump into a pool or your bathtub, you don't fall apart? Okay, because there are bonds, because of this attraction, and because of this setup of atoms. Okay, so let's go to the next one. Okay, we already talked about that one. Let's go here. Let's now talk about bonds. Now, we talked about Na plus and Cl minus, right? Because the Na plus is missing an electron, but the Cl minus has an extra electron. So they're both ions because they're both highly reactive. And we know they're ions because it says, we already showed you the, if you see like something like this, Na plus or Cl minus, you know that they're what? They're ions, they're charged particles, and see that +1 will match up with that -1. And then what will you have? Right? So the +1, the -1, let me repeat that. Why is the sodium +1? Because the sodium in its outer electron is missing an electron. So if it's missing an electron, it's more positive. Now the chlorine, as you see here, 2, 2, and 2, it's got an extra one in its outer shell or its valence shell. that means it's negative. So sodium alone is an ion. Chlorine alone is an ion. Both are charged particles. They're charged particles, and just like magnets, pluses and minuses can attract, and the sodium will be attracted to the negativity of chlorine, and it'll form an ionic bond. And remember, ions are charged particles. Okay, so if I ask you sodium chloride, okay, and I give you this formula, sodium chloride got broken down into water, into sodium plus chloride. And you'll see that sodium is +1, chloride is -1. Then you automatically know that what? Oh, this is an ionic bond. And what is sodium chloride? It's salt. And why are we talking about salt? Because remember, we're 2/3 of us are made of 2/3 of a human being is made out of water. Guess what kind of water? Salt water. All right. All right. Welcome, welcome, Desi. Can you kindly put your full name? If you're not using your full name inside inside the the chat, put your full name in the chat so I know I can grant you attendance and credit for being here. And also, again, I'm going to repeat what I stated earlier. If you're on this call, you don't have. If you're on this call right now and have attendance right now, you don't need to do lesson 1, because guess what? We're doing lesson 1 right now all together in this PowerPoint. So what's likely to happen to the electrons when a potassium atom combines with the chlorine? Let's look at that. Guess what potassium is? Right? K+. That means it is what? It's reactive. It's missing an electron. So what would happen? Let's look at now. In order to deal with what's it called? In order to deal with multiple choice examinations, you got to look, right? You got to look at all the examples, right? So what happens? What do we know that happens? Does chlorine lose an electron and potassium gain electron? Well, that sounds viable, right? Are potassium and chlorine sharing electron? Yeah, in a way they are. Does potassium lose an electron? No, because potassium is +1. So it's not none of the above. It's not C, it's not D. So now we got to look at A and B. And then we got to go back to our definition of what an ionic bond. And if we looked at this definition of an ionic bond, the sodium atom will donate its valence electron so that both of them will have completed valence shells. Both of them will be non-reactive, right? So what it said that sodium electron has 1 electron. It goes, and what was it here? Ionic bond. That means they're what? One has to give up the other. So it'll be even. So here, are they sharing? Nope. What happens in an ionic bond? One has to lose its electron, right? And the other one will gain an electron. And both will be then have complete valence, and both will be inert. And here's a classic example, what we just talked about. So sodium alone, highly reactive. Chlorine gas alone, highly reactive. You don't want to breathe that stuff in. Oh, this is bad news, chlorine gas, right? But what happens if I put it together? I got table salt, sodium chloride, and it just sits there, doesn't it? And that means it's inert. Nothing's gonna go wrong. Nothing's gonna explode. You won't choke yourself to death with the chlorine gas that's gonna bind with all your molecules in your lung, and the sodium won't highly react with anything. So the answer to this, and also a beautiful answer for what an ionic bond is that one has to lose the electron, and that's chlorine because it had the extra electron, and one has to gain one, and that's the potassium. Or instead of potassium, another ion that's also 1+. You can put the word sodium in here. Same thing. All right. So now let's talk about sharing. And this is hydrogen gas, which is a non-polar covalent bond. Now covalent, means sharing. Co, together, valence, right? So the hydrogen bond, they share, and they share non-polar. They share evenly. And that's why hydrogen gas is written H2, right? H with like a little 2 on the bottom. And that's why water is H2O, 2 hydrogens and one oxygen. So if we look at the next question, which of the following is a non-polar covalent bond? Sodium chloride isn't it, right? Because that was ionic, right? We'll be talking, so which out of these where it would share evenly? Well, this doesn't look even. Well, this, we'll talk more about this later, but your best answer would be, let me look at the chat because somebody might, thank you, Miss Massey, thank you, Miss Salvatierra. So what, it goes, what do you think? What does the almighty Google tell you? We definitely know, because we already learned ionic, it's not sodium chloride. And this looks like ionic too, because magnesium is 2+ and oxygen is -2. But you look at here, right? CO2, carbon dioxide, right? That's a gas, isn't it? Right? They share things evenly. So that's the best answer. And remember, this is a classic example, beautiful question. Non-polar, meaning no two sides are going to win, and they both covalently share. Let's now look at something that's polar covalent. Hydrogen chloride, or what do you call it? What's a better one? Well, we'll talk about water in a minute. But if you see here, this is how you know it's a polar covalent. First of all, it's going to look like the non-polar covalent because, oh, look, it's sharing, and it's even Steven. They're sharing 2 between the both. But the problem is, since chlorine is much, much bigger than hydrogen, you're going to have and this is a delta or like a triangle. So you're going to have a positive, a partially positive on the hydrogen side, and you're going to have a partial negative on the chlorine side. And that's how you know, if you see one of these, you automatically think, oh, it's polar covalent because it's uneven. The chlorine is going to win out of this deal. And that's why the hydrogen can easily be pulled away from here. And we're going to talk about polar covalent bonds regarding water momentarily and the properties of it. So right now we learned 3 bonds, 3 things that are keeping you all together. And they all require energy. And they all require either giving up or sharing energy. We talked about ionic, we talked about non-polar covalent, and now we're talking about polar covalent. Okay? And know the difference between the 3. And here's another beautiful one. I just want you to know that water, H2O, and HCl, because this is kind of tricky. It requires for you to know what the valences are for these things. And this isn't a chemistry class, in my opinion. Now, the other example was carbon. That's who we are, okay? So CH4 is methane, right? It's a byproduct of gases. Now, oh, here's the example of water that I wanted to show you. Water is also polar covalent, as we could see here. But the water, H2O, 2 hydrogens and an O, also form this very, very weak bond between the hydrogen and oxygen, and that's called a hydrogen bond. And that's the reason why water is so slippery. this hydrogen bond is also in your DNA. And it's also the reason we're going to be talking about in the weeks to come, why your DNA can be bent, it can be squished, it can be compacted, so that we can fit all the information we need to fit on the blueprint of who you are as a human being. So that's the fourth bond we talked about. And the fourth bond, hydrogen bond, is between a partial positive of hydrogen and a partial negative of something else. And in this case, in water, it's the partial negative of oxygen. Alrighty. Okay. So now we've learned 4 bonds, and let's go back to that thing we were talking about. Okay, I'm gonna write my my concept map. So the main hub or the main spoke or the main part of the concept map would be chemistry, and then you'll have 1 arrow going to what? Types of bonds, and then you'll have 4 arrows going to 1 ionic, 1 nonpolar covalent, 1 polar covalent, and 1 hydrogen bond. And then can there be another arrow giving you an example of each? Isn't that mapping out an exam question that I could potentially have, right? Do you think I could show a picture of this? And then I could ask you, which of the following bonds that will participate in water? A, polar covalent, B, hydrogen, C, both, D, neither. And you now know it's both because I have this partial negative, partial positive, and I also have hydrogen that can attach to this partial negative. And it's a, see this dotted line? It's the weakest bond out of all the ones that we just talked about. And the ionic was the first bond we talked about, and it's the strongest. And then the other ones are, you know, not as strong. Because look at the ionic bond. Look at sodium chloride. What happens if I took a hammer and start bashing salt? What will I get after I start hammering away at salt? I'll have salt, right? It's the same thing with argon gas. I could take argon gas, try to light it on fire, put electricity through it. It won't do anything to it. And of course, in a gas, I could take a hammer to it. It's not going to do anything. It's just going to dissipate. And that's why argon is one of the noble gases. It's not going to react with anything. But if you had a volatile gas, like, I don't know, like car fumes, what happens if it hits a spark or hits some electricity? Then we got a problem, right? Okay, and also, we talked about hydrogen bonds, and I mentioned it, DNA double helix. It's the reason why your DNA can easily be broken apart, easily can be zipped and unzipped and put back together again. And we're going to talk more of that in the weeks to come. And oh, looky here. Do you think I can have a question like this? Right? This one is even Steven. This has to be nonpolar covalent. This one's sharing even Steven, but the chlorine is bigger than the hydrogen. So that has to be polar covalent. This one, you have a partial negative in the oxygen, partial positive. Therefore, it could be, what do you call that? Nonpolar covalent, and it also could be what? It could also be hydrogen bonds, right? That's why this question is a little bit tricky. And lithium and fluorine, you could see that lithium, right? It's missing one, and it had to go over here. So if one had to give up, right? See this gray? If one had to give up to the other one and the other one had to accept it, right? Then that's what? Ionic. I could also ask you, out of these 4, which is the strongest? And you'll tell me this one. Out of these 4, which is the weakest? Hydrogen bonds, this one, right? Between this one and this one, which one's stronger? This one, because it's even Steven. This one's a little weaker because this one, the chlorine is bigger than the hydrogen, and it's not really going to be that even. All right. We already talked about that. Oh, it goes, how many valence electrons? That's easy peasy. You just look at what? Whatever's in the last shell. So 1, 2, 3, 4, 5, 6. So there's 6 valence electrons in a, and this is a sulfur atom. S stands for sulfur. Okay. Oh, look, they have a nice little, you know, chart that you could fill in. And of course, last but not least, Alzheimer's, that will be for your discussion. So let's look at your discussion real quick, and how does it relate to this Alzheimer's? And you really don't need this case. If I read it to you right now, you could pretty much figure out how you're going to be writing. Uh-oh, what happened to my? Okay, so if we go back to the discussion 2, which is due next week. So discussion 2, it asks, based on the completion of the case study, which is that last page of that PowerPoint, complete the application questions on Alzheimer's disease. Well, we kind of did that, but what I would like for you to do for discussion number 2 is talk about how Alzheimer's disease and these bonds and the chemistry, how is that related? How does that produce dementia? And dementia is the progressive loss of memory. So currently there's no cure for Alzheimer's, unfortunately. It's progressive, meaning that it starts out slow and then it gets really, really bad to the point where you become a vegetable and you can't do anything. And the thing that you are to look up for discussion 2 is, what are these beta amyloid plaques that they find in Alzheimer's patients? And what does that have to do with dementia? What does the bonding of these plaques have to do with the dementia? So you're looking for the pathophysiology of beta amyloid plaque. So how does beta amyloid plaque mess up your brain and mess up your dementia? And you don't have to write to 2 paragraphs, one being your introduction paragraph, right? And you could do it in 200, 250 words. A quick introduction paragraph on what dementia is, what's Alzheimer's, and what a beta amyloid plaque. And then the next paragraph, again, based on your citation, right? What kinds of chemical bonds that are in beta amyloid plaques mess up your brain to the point where you have progressive dementia, right? And then knowing that, don't you think your summary would be, well, we could investigate certain drugs, do this, that, and the other thing to break up these bonds? And actually, that is actually the research that is currently going on for cancer, because you have to ask yourself, how does cancer stick to your body? How does cancer keep on growing, right? Why can't we just get rid of it or break it apart? Because if you know how something gets built up, then you could break it apart. Like, for example, we already know what bacteria looks like and acts like. So we have antibiotics that'll do what? Use chemistry to break up or break down bacteria. Hence, the very, very popular antibiotic medication. So that is your goal for this practical application for your discussion 2, okay? Look up beta amyloid plaques and what are they made of, and what kind of chemical bonds that you've learned about that are included in beta amyloid plaques that mess with your brain and gives you dementia. And remember, this dementia, because all of us get older and forget stuff, it's progressive and it's very fast. And here's a classic example. Bear with me if I already talked about my aunt. She's not really my aunt, but she was my mother's lab partner in medical school, and they were best friends ever since. About 6 years ago, she had a practice in San Diego, California, and it's not even 15 minutes away from her home, and she drove there every day for years. One day she called her secretary stating that, trace my phone, call 911. I don't remember how to get back to the office. And it was a very, very scary day for her. And then in the next 4 or 5 months that happened, she was slowly losing her memory. She was a wonderful pediatrician, board certified. And by the time I saw her a year out, she no longer knew the names of her daughters. And the crazy part is, since I was in a white lab coat when I visited her, she thought she didn't know me as her nephew. She knew me. She thought I was one of her attendings. And she called me by a very different name. And it was a very, very sad day. And you could see how debilitating that is. And knowing and understanding how that works, you could see how we could fix a lot of lives if we can figure out really. And right now, 6-7 years later, she's a vegetable. She's got a feeding tube. She has a colostomy tube. She's just there, and there is absolutely no remnant of who she was, and it's very, very hard to watch. So, and you could see all of that because of a beta amyloid plaque, right? So think about that when you're thinking about disease. It's the little things. So that's your discussion too, right? Due next week. And next week, of course, is Tuesday. What date is today? Tuesday, March 30th. So March 30th at 6 p.m. By 6 p.m. on March 30th, what should I see in task 2? I should see a concept map. I should see a 200 to 250 word with one a 7th edition APA citation format for discussion 2. And then lastly, no one here on this call. Let me check the attendance one more time. Oh, I have everybody, I believe, because there are 11 people on this call, plus me, and I have 10 names written down. So if you're on this call, do not do lesson 2. And lesson 2 was to answer those questions and whatnot. So freebie, my little gift to you guys. But do look at that PowerPoint and ask yourself, how can Dr. Garais ask those questions? You know, because that's a really, it's kind of like a giveaway. So we went over basic chemistry. What's an atom? How are atoms put together? We now talked about the different chemical bonds. And I'm in task 2 if you want to know where these notes are. Let's now talk about, what was the next one they talked about? The chemistry of water. And that's this student guide for water. And we recall that water was special because it not only had nonpolar covalent bonding, it also had what do you call that? Hydrogen bonds that it can form. Now, wonderful notes here in these Carolina notes. Cation stands for any ion that's positively charged, like sodium, like potassium. Negatively charged ion, we went over oxygen and chlorine. That's an anion. And when you have something that sounds really alike, memorize one like your life depended on it, and the other one is simply the other one. Like for cation, doesn't that the T look like a plus? So I think plus. Or anion, I had another student who told me it looks like the word onion and onion smell, and that's a very negative thing. So do you see how you use whatever's in your head to remember stuff? We talked about covalent bonds, nonpolar, polar. Now let's talk about water and solubility and Kool-Aid. Let's talk about Kool-Aid. So Kool-Aid is a solution. And what is a solution? A solution is a homogeneous mixture, meaning that once I put the Kool-Aid powder and the water together, can I physically separate it with my hands? I can't. And that's called a solution. And since that solution is in water, it's called an aqueous solution. Now, what's a suspension? Now, if I put chunky stuff in there, that's difficult to separate, but you could kind of see it, and it requires some shaking, like a shake. That's a suspension. And what's a colloid? A colloid, I want you to think of mayonnaise. And mayonnaise, it's a mixture of a whole bunch of things, right? But you could see how it's like no matter how I do it, it's still all mixed up. So let's look at a picture of, so think colloid, think suspension, think, like a shake, like a milkshake. Solution, think like Kool-Aid. And a colloid, I want you to think like mayonnaise, okay? Now, there's different types of solubilities, or how well does the powder or the dry parts dissolve? And the dry parts is called your solute, S-O-L-U-T-E, and the wet parts is solvent. Now, in an aqueous solution like Kool-Aid, the solvent is water. But those of us who are borderline alcoholics, just kidding, or those of us who really love alcohol, myself included, right? When you have a mixed drink, it's in alcohol, isn't it? Alcohol and some water or something like that, you know, shaken, not stirred if you're one of those James Bond types. And it has different solubilities, right? And the solvent for an alcoholic drink is alcohol. The solvent could also be fat, which is the solvent in colloid. Because those of you who know how to make your own mayonnaise, what do you make it with? It's pretty much oil. Oil mixed with egg, mixed with a little bit of vinegar, and I don't want to turn this class into a cooking show. So now, if something is immiscible, right, or insoluble, that means it won't blend with each other. For example, oil and water. Or I put let's say I put a whole bunch of rocks in my drink. Not on the rocks, but rocks from the ground. That's immiscible. I can easily separate that out, and they're insoluble. But if I put salt in water, it'll turn into what? Salt water. And it is, or also known as saline solution, which, by the way, what do you think you're made out of? 0.9% sodium chloride solution or salt solution, also known as NSS or normal saline. Kind of remember that, 0.9%. You'll see that in your pharmacology class. You'll see that in your med-surg classes as you move on, okay? Now, if it's too much, for example, because there's only so much water and so much bonding capability of water, right? Are you one of those people like me who put way too much Kool-Aid powder and then the powder sits on the bottom? That's a saturated solution. That means no more solute or the dry parts or the Kool-Aid can be dissolved. And you'll see what? Powder at the bottom of the Kool-Aid. That's actually how I know that my Kool-Aid is done. That I see a little bit of sugar and I see some of the Kool-Aid on the bottom. Unless you're my wife and my kids who like they barely put any of that stuff in there. That's why they're gross and they're not pleasant people to be around. Now, there are some substances that are hydrophilic. Philia, right, means loving. So there are some things that love water, right? And there are some things that hate water, like oil. Oil is highly hydrophobic, okay? And as I mentioned earlier, another common solvent is alcohol. Please don't drink isopropyl alcohol. It is ethanol or ethyl alcohol is what you drink, not isopropanol. Not good. But they're alcoholics, they'll drink it. So hydrophilic, water loving. Hydrophobic, water fearing. If you have a phobia, you have a fear. Now, didn't you ever wonder how all the parts in your body stay in one side? Now you know. Because of solubilities, because of hydrophilic properties, hydrophobic properties, right? And here we go. I know this is water, H2O, 2 hydrogens and 1 oxygen. It forms a partially positive around the hydrogen, partial negative attraction, and that's what? That can form hydrogen bonds, and it's also nonpolar covalent sharing between the hydrogens and the oxygens. Now, the other important thing about this partial positive and partial negative is that it creates surface tension. If you've ever seen, you know, a mosquito sit on a drop of water, like so. Let's just look at this one. And this is not, don't read this because it'll give you nightmares. You see how it forms like a skin, like a bubble? Well, part of that, right, is we're going to be talking about more when we talk about respiratory function, okay? Because, and surfactant. It gives a surface tension to water, that partial positive, partial negative. And you could see that here. And that's why, you know, nasty mosquito larvae can easily hang out inside there, which is, again, like I said, if you really looked at that, it'll give you nightmares. So that's surface tension. And surface tension is due to the partial negative, partial positive attractions, and it forms this little skin. And that is important to your capability to breathing. And remember the word surfactant. We're going to talk more about that when we talk about our lungs. Okay? So you see all these wonderful properties, hydrogen bonds as well, these wonderful properties of water, right? Another really cool thing about water is its solubility. Image. Now, if you look at, here's a nice thing. If you look at a salt solution, if sodium and chloride is together, right, it forms the little powder, right? Salt. But what happens when I put it in water? It doesn't disappear. Remember the partial negative and partial positive? It's going to pull away the sodium and chloride. And that's why when you sprinkle salt into a glass of water, like this one here, it'll quote unquote disappear. But it's not really disappearing. It's just that the partial positive and partial negative properties of water pulled the sodium apart from chlorine. And that gives it its wonderful property of now I can do what? Put this into a bag and then put this down and put it in your IV and then rehydrate you. Because, and remember, hydration is not only just the water. For those of you who go hiking, what else do you also have to eat? You have to also eat your salt pills, okay? So that is the properties of water, and those are all the cool things that water can do for us, okay? So we already went over bonding. We already went water, basic chemical structure. Last but not least, macromolecules. And that's this right here, number 3, another set of Carolina notes, which talks about digestion. Now, we're going to skip over the digestion part because that's, we're going to be talking more about that when we talk about, what do you call that? When we talk about your digestive, your gastrointestinal tract, right? Because that's the function of your stomach and your intestines and all of them. You have to break down things. Well, I also promised that we'd also talk about chemical properties, and we'll also talk about why do you live? Or how do you live? Well, right now, remember we talked about glucose and oxygen? Those are reactants. I'm breathing in oxygen and I'm eating food to be broken down into glucose. And what is my product? My eventual product, what we'll be talking about in the weeks to come, is something called adenosine triphosphate, or ATP. And the ATP is the metabolic fuel that we need to live. So without any reactants and without this chemical reaction, I don't get to live, right? Now, how does this work? Initially, your body needs a ton of energy, right? So your body has a nice little shortcut, and the shortcut is enzymes. So if you're riding your bicycle, which is easier to travel? Up here, going all the way up here, and then having to go all the way down the hill? Or is it easier to ride up this little hill and then go down this little hill and I get to my products? And of course, the answer is what? The little hill. And that's what we have in our bodies. We have enzymes. Enzymes are proteins that catalyze or speed up chemical reactions. And what's a chemical reaction? Is just what? I put something in the beginning, and then I get something that gets changed or metabolized and then goes to the end. And in the case of a human being, I put in oxygen and glucose, right? And what should I get in the end? I should get adenosine triphosphate, or ATP, and that's what keeps me alive. And I also need these enzymes to speed things along. So for example, how do I know what an enzyme is? Any enzyme will have the suffix ASE at the end of it. So for example, I have a whole bunch of enzymes that will speed up the process that will break down lipids. And you see this, ASE, lipase. And lipases break down lipids. I could also have a protease, breaks down proteins. Again, ASE. I could also have amylase, breaks down carbohydrates, which, by the way, I just now outlined. Fats, proteins, and carbohydrates, which are your organic macromolecules. The fats, they're made out of carbons, hydrogens, and oxygens. The proteins, they're made out of carbons, hydrogens, oxygens, and nitrogens. And the carbohydrates are made out of carbons, hydrogens, and oxygens. That's why when you look at proteins, they sometimes have the abbreviation CHON, or if they're talking about carbohydrates or lipids, they have the abbreviation CHO. You don't call it CHON and CHO, but when you see this, you know it's protein, and you see this, you know it's carbohydrate and or lipid. And those are your three macromolecules. And they're all important. Do you notice I didn't say one was more important than the other? They have to be balanced. So all of these diets that say, oh, we got to get rid of all your fats, or no proteins, or just carbohydrates, like with the original, what's that diet, Atkins 1, is stupid. That person, I still to this day wonder how Atkins graduated medical school or even had his degree in chemistry. Everyone can tell you that if I starve myself of carbohydrates, guess what? I'll start breaking down fats. Yeah, all well and good. But the problem is, you break down fats in a starvation state, you get something called ketones. Ketone bodies are highly neurotoxic. That is why when you starve yourself, you get loopy and you get weird. And that's why you're not you when you're hungry or when you're in starvation state. So along with enzymes, right, that's what speeds up the reaction. Guess what we have to help the enzymes? We have these things called coenzymes. You may know them as vitamins. Where do you get the vitamins from? Not from the pharmacy, not from the store. You get it from eating a healthy, balanced diet, right? You want vitamin C? Eat fruits. You could drink vitamin C all day or take a whole bunch of pills. You're just going to make wonderful orange urine. Now, the really cool thing about these enzymes are they're specific. Like we just talked about. Lipases are specific to fats. Proteases are specific to proteins. Amylases are specific to carbohydrates, right? And it's because they chemically match. And once they chemically match, the enzyme will change whatever the substrate was, or the original, what do you call that? The original reactants, also known as the substrate. And then a new product will get released. Coenzymes, cofactors, also known as vitamins, right? And they're inorganic compounds. That means you don't need tons of it. You know, inorganic means what? They're from the earth. If you eat your share of vegetables and fruits, which I don't, right, which are from the ground, you should have more than enough vitamins. Now, the only time we really prescribe vitamins is if you're much, much older and your GI system is either damaged or not sufficient. But again, that's why we call them supplements. You have to eat and take the vitamins at the same time. Alrighty, and the rest is nice notes for your GI, but we're not going to go over that. So, in conclusion, your whole body runs on these chemical reactions. These chemical reactions, you start off with a reactant or a substrate, and then you end up with a product. And the end product of metabolism is ATP or adenosine triphosphate. The beginning reactants or the substrates, you could see that it's oxygen, not carbon dioxide, oxygen and glucose, which, by the way, what do you think glucose is part of? Glucose is part of your carbohydrates, your simple carbohydrates. So glucose is made out of what? C6H12O6, which is 6-carbon sugar. Okay, and those are your macromolecules. Let's see if they're here. Oh, here they are. Okay, so of course carbohydrates. You think what? Sugars. The monosaccharides are your basic sugars. What are we breaking down everything into? Glucose. It's good. Fructose is good because it's what? It's a basic sugar. Because which is easier to break down? Mono, or something that only has one part, or something that has multiple parts? Like table sugar. That's why table sugar isn't good for you, right? And also, of course, too much of a good thing becomes a bad thing. Proteins. Proteins are a bunch of amino acid chains, right, that get linked together with a peptide bond. And from these 20 basic amino acids, and depending on the order, and guess who tells you which order? Your DNA tells you exactly what proteins to make. And they are also a building block. So they all look the same. They all have carbon, hydrogen, oxygen, and this little nitrogen group right here, or amine group. Okay. Lipids, they're really important because we need fat. It's a buffer. It's also it's a buffering system for as insulation. It also is really important in storing what do you call that? In storing glucose. That's what we break down if you're eating regularly. But like I stated, if you're starving yourself, your insulin won't break down lipids. The insulin will tell your lipids to make ketones, and like we mentioned, that's not a good thing. So triglycerides, steroids, phospholipids, waxes, these are all important things. But remember, too much of a good thing becomes a bad thing. Too little of a good thing is also a bad thing. You have saturated and unsaturated fats, and the saturated fats, right? These are the ones that are not so good, like coconut oil, and they're solid at room temperature because they have covalent bonds, nice, stable, sharing bonds. But unsaturated have double bonds, and they're generally liquid at room temperature, and in general, they're better in your health and easier for your lipases to break down versus your saturated. And last but not least, the last macromolecule we'll talk about is the nucleic acids. You have DNA and RNA. DNA is the blueprint of who you are, and RNA is like kind of like the messenger. But we'll talk more about DNA and RNA. And here's that word, adenosine triphosphate, right? ATP is also part of the nucleic acid family, and ATP is your molecular currency or your molecular energy. Currency means money, right? And it's your energy, what powers you. Without glucose and oxygen being pumped into your body, you won't make ATP. You won't be able to move your muscles. You won't be able to breathe. You won't be able to do anything. And that's the real thing that powers you. Now, let's go back and let's see. Did we do everything? Did we talk about the basic chemical structure of organisms? Sure. Did we talk about macromolecules? Yep, we just did. The 4 macromolecules, which is the DNAs and RNAs and ATPs of the world, which is the nucleic acids. You have lipids, lipids, which are fats, proteins, and carbohydrates. And we talked about the different types of bond. We talked about 4 different kinds of bonds. And we talked about what's so special about water. Now, let's see. Let me just check one more time. to see if Miss De Leon is in. And she's not in yet because she's in another meeting. But hopefully, if I end, maybe she can come in at 7:30. So let's see. So let me go over on how I would make a concept map. Now you can also just Google it, YouTube, because YouTube solves everything. I told you guys about my bathroom, right? How many times concept map for nursing students. All right. You could click on any one of these videos, how to make a concept map, right? Now this thing, not so good, right? Because it's like too much words, but let me show you how I make a concept map and how actually it's in my opinion, it's like the easier and it's a neater, nicer way. Now you could also make it like wide. So I could go on Microsoft Word and put the layout, the orientation here sideways. And then you could draw, free-handed. But what I like doing is you go into insert, you go to shapes, and you get a shape. And let's put it like right smack dab in the middle of my paper. And what's the topic for today? It's week 2. And the topic today was chemistry. And then what were my 4 topics? Well, right here, if you saw it here, basic chemical structure. So do you think I could just keep on adding other circles? I put a circle here, right? I could take and copy this, and then paste it. Why invent the wheel? And then keep on pasting it. Put another one here. And another paste it here, put another one here. And weren't there my 4 topics? So can I have this as I click on the middle of that and write basic structure? Hey, could I click on this one and talk about macromolecules? Make it a little bit bigger so I can, or I can make, great, I don't know how to spell, macromolecules. Or I can make this, and then you can go to home and make it smaller. Right? And then this one was what? Bonds. And then this one was water. And then you go back to draw, or not draw, but insert. I go back to shapes. Hey, they got them arrows here. I just click and drag, point arrows. And do you see how much neater this is? And it doesn't take much. And look how it organizes your mind. Now you could see visually what it looks like and what I need to study. Have you ever looked at your notes and then you totally forgot that there's notes on the other side of the page and you didn't even bother studying that section, and then you get a whole 5 or 6 wrong? Well, this is to assure you that you don't get anything. Now in basic structure, I guess I'll put atom, smallest building block, and then another circle here with an arrow, neutron, proton, electron, right? Macromolecules, I'll put the 4 little circles, right? And the bonds. I'm pretty much telling you exactly how to do it. And in the bonds, the 4 bonds that we did, ionic, and then with an example. So you can go on and on and on. But do you see how much neater it is? And then, of course, kindly make sure you put student name. It goes the course, which is MED110 or whatever. Or you could either write it in there, or here you could also insert text box. Click and drag. Oopsies. Insert text box, please. Draw text box. Right here. I also had another student just draw text boxes and then just put arrows. And then for the different concepts, what she did was make the letters different colors. So it's at this point of the show where I turn off the recording and then I